to make sure that our unification schemes accommodate, and also the opportunity to make sure that our unifications accommodate and illuminate this peculiar structure of the standard model, which is so successful and reasonably compact, but not as compact as nature's last word should be. So let's start with SU5, which is smaller and a little easier to visualize. The SO10 mathematics is fascinating, as you'll see, but it's better to approach in stages. So SU5 is the group of unitary transformations with determinant 1 in a 5-dimensional space of complex numbers. It can be written in terms of 5 by 5 matrices. It usually is written in terms of 5 by 5 matrices. And that immediately suggests how SU3 cross SU2 cross U1 can fit in very compactly. Let me make this one a little bit bigger. Okay. So we have a 3 by 3 and 2 by 2 matrices that are unitary transformations. If we just take entries in here, we get 3 by 3. We get unitary transformations in 3 dimensions, so that's U3. The determinant is not necessarily 1, but we can certainly fit SU3 there. And we can fit SU2 here. And now let's take into account the determinant equals 1 condition. Okay. We want to take into account that within SU5, you can get determinant 1 for this product, even though separately they don't have determinant 1, but have overall phases. Namely, you can have on top of this SU3 and SU2, and commuting with it, transformations of the kind e to the minus I 2 times theta, just along the diagonal, e to the minus I 2 times theta, e to the minus I 2 times theta, e to the I 3 times theta, e to the I 3 times theta. Okay, the total determinant is 1, even though the subdeterminants are not 1. This is a 1-parameter abelian group that commutes with everything else that we're interested in. So this gives us a U1. And that's how SU3 cross SU2 cross U1 fits very, very snugly into SU5. Yes?
No, it seems like from that decomposition, then you get this 1/3, 2/3 numbers, right?
Well, yeah, you can see the germs of 1/3 and 2/3 coming in.
Well, that's where they come from, right?
Well, ultimately, yeah. We have several steps to go, but yes.
But then I wonder, is that a unique decomposition in a way, or are there many other decompositions?
No, this is completely unique. If you want transformations that are in SU5 and that commute with SU3, this SU3, and this SU2, that's all there is.
There's no other way to fit in.
Nope.
Yeah, okay.
Nope. Of course, you could make much bigger groups, then you have many, many more options. But the fact that this one works already as well as it does is an indication that you don't want those options. Right, to me, I think, yeah. Also, the fact that, as you'll see, the fermions fit in very nicely indicates that you probably don't want to consider much bigger groups because they would give you extra fermion. The multiplets would have extra fermions with exotic properties that we don't see in nature. Okay. If we take the infinitesimal form of this, to go from, so to speak, gauge transformations to charges, we see that the hypercharge generator will be some constant which is not determined. So this is the hypercharge transformation. The hypercharge generator, which generates the charges for the different particles by acting on it, will be proportional to this guy, with of course zeros everywhere else. Just that along the diagonal. Okay. C is a constant to be determined by fitting to the observed spectrum. But we'll have to make sure the same C is used in every case. So at this point, I'm going to write down the answer for SU5 and then justify it. Okay? If you were discovering this as opposed to explaining it, you would play around. Let me just, to see what fits, let me just say that there aren't a lot of choices. Remember, we're trying to accommodate either 15 or 16 degrees of freedom into a few multiplets. These simple multiplets that you can have under SU5 are, of course, singlets. But if you have too many singlets, that's very disappointing. You're not really unifying anything. So those are one-dimensional guys. You can have the vector representation, which is 5-dimensional for SU5, or, of course, the inequivalent anti-vector representation, upper or lower indices. And the next smallest representation is the 2-index anti-symmetric tensor. So it's anti-symmetric, so this has 5 times 4 divided by 2 independent indices, or 10, or it's the lower case. If you take the anti-particle version, the lower index version, you'd have a 10 bar, so-called 10 bar. All the other representations are too big. They have more than 15 or 16 dimensions. So really, these are the only candidates, and we have to build our fermion multiplets from these. There aren't very many choices. If you want to get to 15, you have to have 3 of this kind, or 1 of this kind and 1 of that kind. The choice that works is 5 bar plus 10, as I'll now explain. And if you want, as an exercise, you could show that the other ones don't work, that don't fit the observations. You would go through the same kinds of steps, except the numbers wouldn't work out. So let's see how 5 bar plus 10 fits the 15 degrees of freedom, leaving out n. That's going to be a singlet. In fact, it has to be a singlet under SU5 because it's a singlet under SU3 and SU2 and U1. So we're going to, but we'll get all the other guys fitting into 2 multiplets. Now, if we're going to put different particles in the same multiplet, the sum of their hypercharges has to vanish, okay? Because this generator, if you, no matter how many indices you have on it, the sum of all the things it acts on is going to be 0. This reflects the fact that it's that the overlying determinants inside SU5 are determinant 1. There's no extra phase. Okay. So we have to look for combinations where the hypercharges add up to 0. And one combination that works, there aren't very many that work, but one combination that works is this stuff. Okay, we have 3 times 1/3 plus 2 times minus 1/2 being 0. Okay, there seems to be a problem, however, if we want to realize SU3 and SU2 as acting on vectors of SU5. We want either both of them to have upper indices or both of them to have lower indices so that they can organize into a coherent vector under the bigger group. But that is actually not a serious problem, because within SU2, vectors and anti-vectors are equivalent. If we have a 2-dimensional vector R sub A, we can trade it in, if you like, using the invariant anti-symmetric symbol for an R sub B, or if we have an R sub B, we can trade it for an upper index thing. Okay. So just by rewriting things in this way, you can, instead of using this field, use the same thing contracted with the invariant symbol. So it doesn't upset the group theory, to just lower this index. And so I'll do that. Okay. So then these fit into a 5-bar representation, an anti-vector with lower indices. And to fit the hypercharges, if this is going to be lower indices, we need that C times a minus sign, because we're using lower indices for the 5-bar representation, times minus 2 equals 1/3. So This is all acting on the three components of D bar and the two components of L this way. So this has to be equal to 1/3. And similarly, C times an overall minus sign times 3 has to give us the minus 1/2. And both of these are consistent. That was kind of built in because we wanted these to add up to 0. But they're both consistent with C equals 1/6. So we determine that number. That number, by the way, will be very, very important when we come to talk about the quantitative aspects of how the coupling strengths of the different interactions unify. But in any case, this fixes the one undetermined number in this unification. Okay. Now we have all the other guys. The leftovers. So I'll put round groupings around. There are 10 of them, 10 components. So we'd like to match them with the 10-dimensional representation, the two anti-symmetric index representation. Shall write now T out. I'll write T mu nu was the original anti-symmetric tensor. If we want to analyze its, so that's how it is under SU5, all the indices are equivalent. If we want to analyze its structure under SU3 cross SU2 cross U1, so we can identify it with stuff in here, we have to look at the different parts of this, and there are 3 different parts. There are parts where we have one color and one, well, let's raise this. We can have 2 indices which come from the first 3, so 2 color indices, or we can have 1 color and 1 weak isospin, or we can have 2 weak isospin indices, like that. Those are the 3 different possibilities. Okay, let's count how many degrees of freedom these have. This has 6, because 3, it's anti-symmetric. 3 times 2 divided by, I'm sorry, this has 3. 3 times 2 divided by 3. This has 6, 3 times 2. There's no anti-symmetry since these are different types. And this has 1. Okay, so in order that those should correspond with these guys, what we need to have is that this matches the quantum numbers of Q, the 6, that this matches the quantum numbers of U bar, very good, and that this matches the quantum numbers of E bar. Well, Q is easy. Okay, it has just the right structure. We don't have to massage it at all. The only thing to check is the hypercharge. Well, if we have the hypercharge operator acting on one of these and one of these, we get a sum of one of these and one of these. We add up and then multiply by 1/6. And lo and behold, that's exactly what we find in nature. Whoops. Over here. So that's good. That's this one is also easy. Okay. If we have two anti-symmetric indices that run from 1 to 2, there's exactly one component. It's so it's a singlet. It's proportional to the epsilon, the invariant epsilon symbol we stumbled into before. So this indeed is a singlet under SU2, manifestly a singlet under SU3, and its hypercharge we get by adding up two of these, 3 plus 3 divided by 6, 1, which is what it should be. And then finally, this one is a little bit tricky. We have two anti-symmetric color indices, so that makes a three-dimensional representation all right. But we've come across it in a different way here. Fortunately, if you take epsilon, you use the same trick, an epsilon symbol, now with three indices, to trade a two-index anti-symmetric tensor for equivalently a one-index anti-vector. So it looks different, but the difference is something that's trivial as far as SU3 is concerned, and SU2 and U1 don't care either. So we can trade, so we can identify this with U bar. We have to check the hypercharge. Well, the hypercharge is two of those top ones. So -2 plus -2 divided by 6 is minus 2/3, which again is just what it should be. Okay, so SU5 in this very natural and unforced way fits this scattered structure of the standard model and explains the relative values of all these hypercharges. Instead of having 5 different entities, we reduce to just 2. And instead of having all those funny numbers, we just have one overall normalization.
Because you probably get it -3 2/3.
It's -2 plus -2 divided by 6. Okay, so now let's move on to SO10. That's how SU5 works. SO10 is very interesting also for those of you who are Majorana neutrino fans or exotic fermion fans, because it gives us a chance to introduce spinors and the mathematical techniques for dealing with them, Clifford algebras. What's that?
Are there any predictions besides putting things together?
There are predictions. I'll come to that next time. Yeah, so predictions include, well, predictions, if you take it to, well, I'll need some further development to make these into predictions, and they're really much more compelling within SO10 but predictions include what the strength of gravity is, that neutrinos should have small but non-zero masses, the relative strengths of the different couplings. If you have low energy supersymmetry, so it also predicts low energy supersymmetry for it to work. And also, what's that? So far there's no mention of supersymmetry, right? That comes into the quantitative aspect next time. So supersymmetry just is another commuting symmetry on top of all this. So it doesn't interfere with it, but it also doesn't change the analysis. The other prediction is that protons should be unstable. So we're waiting on that one. So there are quite a few predictions, actually, and with more assumptions, there are relationships among the masses of different fermions and things. So there are lots of predictions. And if supersymmetry is discovered, there are predictions for the relative masses of different supersymmetric particles. So I would say that if, and basically only if, low energy supersymmetry is discovered, we'll get many tests of this better. And the first one is that low energy supersymmetry should be discovered. So also to finish up on that question, you might ask, of those successes, how many were predictions as how many were kind of assumptions? I would say that the fact that the unification scale turns out to be essentially the Planck mass, so that gravity also unifies, is a prediction. That wasn't an assumption. And the fact that the different coupling strengths all derive from 1, that's a prediction, definitely not an assumption. And then finally, the existence of small but non-zero neutrino masses, that was a prediction. That was predicted before the observations. So,
But it doesn't predict the mass ratios of neutrinos.
doesn't predict the mass ratios, and it's only semi-quantitative. It predicts they should be very, very small, but not exactly how small. Okay, so on to SO10. I'll try to be reasonably concise about this. If you really want to master it, I'm afraid you have to sit down and do some algebra and get it clear in your mind yourself, but I'll at least give you some guideposts to this extraordinarily beautiful chapter of mathematics, I think, that every physicist that should know and is becoming extremely fruitful, not only in particle physics, but also in condensed matter physics. So, the Clifford algebra is defined by anti-commutators of the form gamma j, gamma k, anti-commutator, so gamma j is 2 times the Kronecker delta jk. If you had 0 on this side, you'd have Grassmann numbers, anti-commuting variables. So this is the quantum version of Grassmann numbers, where you have like an IH bar over here, you have a non-zero commutator. And actually, that's not just a joke. If you work through the quantization of fermions, fields, the classical theory is based on Grassmann numbers. The quantum theory introduces a non-zero right-hand side of this form. One can also instead of delta jk, include forms which have some ones and some zeros, and that's very important. Some ones and some minus ones, and that's very important in the Dirac equation and in relativistic theories. But at the level of algebra, it's pretty straightforward to go from here to here. And for purposes of this lecture, we want this one, this version. And although it's interesting, I don't want it. This would be a diversion. So it's like it's Euclidean space, right? It's the metric of Euclidean space. And again, although one can do it with different numbers of indices, and a lot of the structure is the same, although there are interesting little wrinkles that do depend on the dimension, especially when you consider Majorana and Weil conditions. The case we'll be interested in is these indices run from 1 to 5. I'm sorry, 1 to 10, of course. Another way of thinking about the gammas, the way Dirac originally introduced them in the Dirac equation, is to think of them as taking the square root of the metric. Here we're taking the square root of the Euclidean metric. Okay, so the gammas can be realized as Hermitian matrices. All of them have squares equal to 1, and they all anti-commute with each other. That's saying the same thing in words. Okay, to get a grip on these in terms of concepts that physicists are very familiar with, and a very useful way of moving back and forth between fermions and things described by gamma matrices is to introduce complex linear combinations of nearby gamma matrices. Because in terms of these objects, the Clifford algebra becomes just re-expressing these relations, or in terms of the A's, becomes simply alpha j, alpha k dagger equals 2 delta jk. AJ, I shouldn't say alpha, I should say AJ, AK equals A dagger J, A dagger K equals 0. So out of the 10 gamma matrices, you construct 5 fermion creation and destruction operators, and vice versa. Now, the connection of the Clifford algebra to rotations is that if you define RJK equal to 1/4 the commutator of gamma j and gamma k. So define that way. Then if you calculate the commutators of the RJKs, they are isomorphic to, they match the commutators that you would get for rotations, infinitesimal rotations, in the JK plane in a 10-dimensional space. Okay, if you generalize the way you get angular momentum in 3 dimensions by thinking about commutators of rotations in different planes, you can easily generalize that. Don't try to visualize it too hard, but you can easily generalize it to rotations in a 10-dimensional space. Figure out what their commutators are, and they exactly match the commutators that you get by following this algebra and applying it to these guys. That means the implication of that, the big implication, is that a representation of the Clifford algebra gives you a representation of the rotations. A representation of the Clifford algebra with n gamma matrices gives you a representation of the group of rotations in n dimensions. This gives us a different kind of representation than we get from vectors. So it's fundamentally new. It's something that occurs only for rotation groups, not for unitary groups. For example, we have additional kinds of structures that are inherent in the nature of rotations that are not at all obvious, but turn out to play a very important role in many branches of physics. Now, more accurately, just as a fine point to mention, what you get is a representation not of the group of rotations, but of the infinitesimal rotations, the Lie algebra. If you want to go to a group, you really have to go to what's called the universal covering group of the rotation. So this is familiar in the case of 3-dimensional space. The spinor representation is not really a representation of the rotation group, but of its universal cover, SU2. Okay. But for our purposes, we can just look at the infinitesimal version, and that fine point doesn't really arise. RJKs are the generators of the infinitesimal generators of rotations.
Gamma is the dimension of the
Excuse me?
matrix gamma. The dimension of the matrix gamma is
Right now, you just
Oh, well, and now they're just abstract symbols. It'll turn out
the JK is a bit like a space-time that we
Well, yeah. Let me show you. Okay.
Is there a size, like in 4 space-time dimensions?
Come again?
Again, we know that I think in 4 space-time dimensions, yeah, is gammas that minimum size 4 by 4.
Yes.
So in that
Okay, I'll show. Okay, let's look at. So to form n-dimensional. And let me look at even dimensions only. That is, to form matrices that satisfy the Clifford algebra. Let me show you how you do it. So we'll take gamma 1 to be sigma 1 cross identity, cross identity, cross identity, cross identity. The square is equal to 1. Okay, I hope this tensor notation is not too scary for people. Just means you have 5 indices. Each of these acts on one of the indices. Each index has 2 components. And gamma 2 is sigma 2 cross 1 cross 1 cross 1 cross 1. And now we might be tempted to put gamma 3 equal to sigma 3, but a better way, and that would be fine if we just had 3 dimensions, but a way that allows us to keep going is to have sigma 3 and then sigma 1. Because we want to be able to have something that anti-commutes with the next guy. Okay, so these guys will all anti-commute with each other, and all of them square to 1, which is what we need. And now we can do gamma 5 by having sigma 3 cross sigma 3. And then I think you get the idea. So finally gamma 10 will be sigma 3 cross sigma 3 cross sigma 3 cross sigma 3 cross sigma 2. Okay, that's one particular representation of the gamma of the Clifford algebra. It has 2 to the 5th equals 32 dimensions. That's for p equals 5. If we for larger p, we'll just get 2 to the p. So unlike vector representations that grow like n in dimension, these spinor representations grow exponentially in the size of the rotation of the space. Now, I've just written down this representation from out of the blue. I haven't proved it's unique. I haven't proved it's irreducible or anything like that. With some work, you can show that it's almost irreducible and almost unique. That is unique up to isomorphisms and not quite irreducible. It turns out that all these guys anti-commute with sigma 3 cross sigma 3 cross sigma 3 cross sigma 3 cross sigma 3, which in fact is basically the product of all of them. Well, yeah. This is the analog of what you would have as the gamma 5 in the theory of the Dirac equation. That gives you chirality. But in any case, we just see straightforward by algebra that this anti-commutes with all of these guys. That means that it commutes with the R's, which are quadratic in the gammas. So we have this thing that commutes with all the R's, which means our representation is not quite irreducible as far as rotations are concerned. We can take either the plus eigenspace of this or the minus eigenspace. Its square is 1, so it has two eigenvalues, 1 and minus 1. Both eigenspaces will be invariant under rotations, and they give us 16-dimensional representations. In fact, they're not equivalent, so we call them 16 and 16 to bar. Those are irreducible, and this 16, that's the magic number of degrees of freedom that we want it to fit, remember. Okay, so you asked, I told you this is explicitly how you can construct the representation and its dimension. Let me, with that in the background, yeah.
So you this algebra, I mean, standard, people worked out already.
Oh yes, no, in fact, yeah, this was discovered essentially by the mathematician Cartan in the 1920s. Although many of the detailed structures, like Majorana, whether you can have Majorana or Majorana-Weil, and what happens if you include some minus signs and so forth, I think are more recent developments. It's a fascinating, although rather abstract subject that I could easily give another 2-hour lecture on. I'll put out, I have notes on this, so I can easily distribute.
In the field theory book, this is not included.
No, you wouldn't find this in the typical field theory book. No. Field theory, and when you look at the theory of the Dirac equation, or for that matter, the theory of rotations in 3 dimensions, when you discuss spinors, those are special cases, can be regarded as special cases of this theory, but they're sufficiently simple that people just usually do them by hand, rather than developing the full theory and using and calling them a special case.
So how did you come across to this one?
What?
So you were looking for the Majorana, you were looking at the mathematicians' result. So how did you find this one?
How did I find this?
Yeah. Not even-
Well, I took, I didn't, all of this was known in some form. If you're asking how I personally developed it, I looked at some special cases and generalized it in a way that I could understand. And so this particular realization with, all this level of detail and these particular notations, I don't think you'll find anywhere except in my notes.
Yeah, that's actually
All right. All right. So, and I think it's the clearest, obviously correct way to do things, but other opinions may differ, right? All right.
So this is a kind of a very, this is really original. From
No, I wouldn't overdo it. I certainly wouldn't overdo its originality.
But
So
you basically reorganize the
it has some pedagogical novelty, perhaps. That's
This is one
yeah,
of
yeah,
the-
right. Yeah.
You first came up with this idea of SU5? There was an
SU5 and SO10 are both due to Georgi and Glashow. Yeah. I mean, as unification groups for particle physics.
The
Well-
reason I like this one is people can use the like two spin states
Yes.
as the basis.
Yeah. Oh, yeah.
Just like all this-
Absolutely. Right.
And
yeah.
this is the way you use the two spin states.
Yeah. Yeah.
Represent all this.
Yeah. It's very.
Uh,
This, by the way, if you know your 1+1 dimensional solvable models, this is very much like the, what is it called? The Wigner, Wigner construction, where you change spin systems into fermions and vice versa. Jordan Wigner, yeah, Jordan Wigner, right. And the fermions have tails. Those are these sigma 3s. So this is also closely related to Jordan Wigner. It's closely related to all kinds of things, like error correction in quantum computing, turns out, unified.
You also mentioned the block spins. High spins can be represented by the spin on half.
Yes, certainly higher spins can be represented as, in terms of, yeah. That's a slightly different direction, but similar in spirit. Okay, so we were, before this very long but useful digression, we were talking about the fermion structure, in fermion avatars of the Clifford algebra. Which were these A, J equals gamma 2J minus 1 plus I gamma 2J. I think there was a plus. And AJ dagger equals its, oh, this was minus. And AJ dagger is complex conjugate. That's Hermitian conjugate, right? Okay, and these obey fermion creation and destruction. So it's as if we have 5 fermions. The 5 dimension. That's another way of getting the dimension, by the way, which may be more intuitive. If we have 5 independent fermions, each of the states can be occupied or not. That's another way of getting the 2 to the 5th equals 32. Represent them as occupancy of 5 fermion states, and yeah, so as I said, if you take since we can express the gamma matrices in terms of these fermion creation and destruction operators, we can represent the way they work in an alternative way as operations within a 32-dimensional space of fermion occupancies, namely 0 or 1 for 5 different fermion states, so 2 to the 5th. To get that's not quite irreducible under rotations. The point being that, let me remember. The point being that, yeah. So we get a 32-dimensional space. Which we constructed in one way over here explicitly in terms of the gammas. We could equivalently get a 32-dimensional space by representing 5 fermion states that can either be occupied or not, and let the A's act on those. Let the A's be creating and destroying these 5 different fermions. That's not irreducible, though, because it turns out if you write down the R's, remember the R's are commutators of gammas. The gammas are linear in A's and A daggers. So these things will either have 2 destruction operators, or a creation and a destruction, or 2 creations. In any case, they will conserve fermion number modulo 2. Okay, so the fermion occupations that are either even or odd will transform separately under the rotations, and those are 2 16-dimensional representations. That's another way of seeing that you have a 16 and a 16 bar representation. Okay, it's getting late, but fortunately I can make the main points very concisely now because of all the work we've done, and in particular the work we did previously with SU5. So as I was just saying, this gives 3 kinds of terms in general. We get AA terms, AA dagger terms, and A dagger terms with different indices on these guys. We can look for combinations of R's that contain only AA daggers, or to put it another way, that conserve the fermion occupancy number. So for instance, a simple one is R12. This is the commutator of things like A1 plus gamma 1. No, I'm sorry, yes. It's the commutator of gamma 1, gamma 2, and gamma 1, gamma 2 are A1 plus A1 dagger, A1 minus A1 dagger. They're the Hermitian versions of these creation and annihilation operators. And you can easily see that this is proportional to A1 is equal to a combination of A1 dagger and a number. It doesn't have double creation or double destruction operators, clearly, because the commutators there give 0. It's only the cross terms that survive. And so this is an example of something that conserves fermion occupancy number. So are R34, R45, R56, R78, and R910. In fact, this one gives basically just counts the fermion number occupation in the first slot, second slot, third slot, fourth slot, and fifth slot. Okay. Then, as described in the notes, or I highly recommend you fiddle around with it a little bit to identify, there are other combinations like R13 plus R24, which also conserve fermion occupancy number because the double A and double A dagger terms cancel if you do little calculations like this. Okay? And if you work through the whole thing, you find that the R's that remain generate the rotations that conserve fermion occupancy number. There are a lot of them. They generate an SU5 subgroup of SO10. It's very natural that they should, actually, because if you think about 5 equivalent fermions that you can rotate among one another, not changing their number, but rotating them one among another, that should be an SU5 group, and that's the SU5 group you've got here. Actually, it's not quite SU5, it's U5. Because there's one generator that counts the overall occupancy of everything. That's special. That commutes with everything else. Commutes with things that change one fermion into another. Okay, so we have a nice fat SU5 subgroup of SO10. We just analyzed SU5 and seen how to identify particles or entities within the standard model as components of SU5 multiplets. So all we have to do now is see that the SU5 multiplets we wanted from SU5 fit together into an irreducible multiplet of SO10. Okay, so let's look at remember the two irreducible things we got in terms of fermions, the two irreducibles were even occupancy or odd occupancy. of our 5 fermion system. This is irreducible under SO10. So let's see what their content is under SU5. Under SU5, the different occupancies are separately irreducible. So when we have even occupancy, we have one SU5 multiplet which corresponds to 0 occupancy, another that corresponds to 2 occupancy, and another that corresponds to 4 occupancy of the fermions. Whereas if we have the odd occupancy, we can either have 1 or 3 or 5. Now, what do these correspond to? Again, SU5 is mixing up the different fermion labels, transforming one kind of fermion into another. The fermion representation is antisymmetric under interchange because we constructed it from fermion creation and destruction operators, which anti-commute. They're proper fermions, they anti-commute. So this gives us an antisymmetric tensor of SU5. This gives us a 4-index antisymmetric tensor under SU5. This, of course, gives us a singlet. So we get the antisymmetric tensor that we wanted. And this one, now using the trick that we used previously for SU2 and for SU3 to move indices up and down using the epsilon symbol. We use it again here. This is equivalent to a 1-index vector or rather anti-vector with a lower index. Okay. Another way of checking is that this has 10 times 9 times 8 times 7 divided by 4 times 3 times 2 times 1 independent components being antisymmetric. And if I'm lucky, this will turn out to be 5. No. What's going on? Oh, I'm sorry. This is stupid. 5 times 4 times. It's SU5, SO10. Divided by 4 times 3 times 2 times 1. Antisymmetric has 5 indices, as indeed it should. Okay. So, just as in SU2, a vector was equivalent to an anti-vector, or in SU3, a 2-index antisymmetric tensor was equivalent to an anti-vector. Here, a 4-index antisymmetric tensor is equivalent to an anti-vector. And so, this structure gives us, under SU5,